Good evening, everyone. In the last class, we discussed about the condition for equilibrium of different charges, and we also discussed about the superposition principle, and uh, where we try to find the electric field due to where we try to find the force on a given charge because of the presence of n number of other charges. In this lecture today, we'll be discussing about the electric field intensity, what actually electric field is. Suppose that we have a charge q here. This is the charge q, and this is the region around this charge. And this is the space around this charge. We have charge q plus q and the space around this charge. Suppose I'm placing another charge q naught in the space of this, in the region of this charge plus q. And suppose that this charge q is placed at a distance of r. Or we can represent this position of this charge q naught with respect to this charge plus q with this position vector, that's r vector. Here this r vector is nothing, it's r into r cap. Here r cap is the unit vector along this r vector, and r is the magnitude of this vector. So if we place any other charge in the space of a given charge, then what happens is that electric force is experienced by this charge q naught, and this charge q naught experience an electric force because of the presence of this charge plus q. Because of the presence of this charge plus q. So what happens is that this plus q charge creates a field around it. It creates a field around it. What is that field? It's a space around this charge plus q. And in that space, if we place a charge plus q naught or any other charge, and this charge is going to experience force. This charge is going to experience some force. So electric field intensity is nothing, it's the space around a charge or charge distribution. It can be a point charge, it can be a charge distribution as well, where any other charge when placed around this space, in this space, experience some electric force or the electrostatic force. And this space and this force, this electrostatic force experienced by this unit charge, electric force experienced by a unit charge or test charge. And this electric force experienced by this test charge is what we call as the electric field intensity at that point. For different points in a space around a charge plus q, the electric field intensity will be different. This electric field intensity is characterized by some properties. It's a function of a vector. It's a function of a vector, function of a position vector. So we have this is the position vector here, r vector. Suppose that if this charge q naught is placed here, the position vector will be like this. Let me call this r1 vector. So it will be nothing, it will be r1 into r cap. So it's clearly the position of a function of a position vector. For different position vectors, for different positions around the space of charge plus q, the electric field intensity will be different. So that's the reason we say that it's a vector function of position. Electric field intensity is a vector function of position. And it is also a scalar function of position, a scalar function of position, or it's also a scalar function of potential. Electric field is also a scalar function of potential, and later on we'll see that electric field is defined as the partial derivative of this potential V, where this V is nothing, it's the electric potential. So in nutshell, the electric force or the electric field intensity is nothing. It's the space around a charge. When we place an external charge in that space, and that external charge is going to experience some electric force. And the intensity of that electric field is given by the amount of electric force experienced by that test charge or by a unit charge. So that's what we understand by the electric field intensity at a point. And the electric field intensity is also represented graphically by the, it's given the it's represented by the pictorial representation by the electric field with the help of electric field lines, with the help of electric field lines, with the help of electric field lines. We give the pictorial representation of this electric field. It's just the geometrical representation. It's not like something that field is actually like that in the space. It's just the geometrical representation. Like if we place a test charge in that at that point in that space, then how the electric force is going to act on that test charge in the space of charge plus q. Suppose that this is the plus q charge here, and we're placing a plus q naught of test charge here at this point. And the position vector of this charge q naught plus q naught, that's r vector, and it's defined by r into r cap. Here r cap is the unit vector of this plus q naught in the direction of this plus q naught. So let's suppose that force Fx on this charge plus q naught, which is a plus q naught is a test charge. Q naught is a test charge here. Q naught is a test charge. And we'll see what test charge actually means. Q naught here is a test charge. And this Q naught, this is a plus Q point charge, and this plus Q naught, it's a point test charge. And this is going to experience a repulsive force because of the presence of the same sign of this charge plus Q. And the direction of that electrostatic repulsive force will be along this position vector r cap. Along this position vector r cap. Let me define this, the net force acting on this test charge is F. It's given by F. And this F is nothing. It's given by the field present here. Suppose E is the electric field intensity here. Suppose that E is the electric field intensity because of this plus Q charge at this point where this test charge is placed. Then the force acting on that test charge Q naught is given by Q naught times the electric field intensity at that point. Where E is nothing. E is equal to electric field intensity. Electric field intensity. And this electric field intensity is because of the presence of this charge plus Q. It's because of this charge. So E is nothing, it is electric field intensity. And if we multiply this electric field intensity with the charge Q naught, we will get the force acting on this test charge plus Q naught. If we talk about the SI unit of this electric field intensity, it is nothing. It's given by force upon Q naught. So this force is the force acting on this charge plus Q naught. Force is the this F is the force which is experienced by this test charge plus Q naught. And upon the charge Q naught, this will give us the electric field intensity. Field intensity. This will give us the electric field intensity at this point. So at different points, suppose that same charge plus Q naught is placed at here, at this point. And the position vector from this plus Q and this Q naught is R vector. That's equal to R into R cap. Now this position vector is now different than the previous one. If this position vector is different than the previous one, it means that the electric field intensity here at this point will be different than the case first. Or we can say that The electric field intensity will be different at different points, or we can say that electric field intensity is a function of position vector. It's a function of position vector. For different position vectors, the electric field intensity will be different, because for different position vectors, the net force acting on the test charge will be different. But that's the reason the electric field intensity will get a different magnitude of the electric field intensity at different position vectors. So let's suppose that the force acting on this plus Q naught charge at this point is F2. And this F2 force will be nothing. It will be the test charge Q naught multiplied by the electric field intensity at that point. Let me call that electric field intensity is E2. So this E2 will be nothing. It will be the force experienced by this test charge at that point upon the charge Q naught. So this will give us the not only the electric field magnitude of the electric field intensity, but also the direction of that electric field intensity. So from here, the SI unit of force is Newton, and the SI unit of the charge is Coulomb. So the SI unit of electric field intensity, it's nothing. It's Newton per Coulomb. So this is the SI unit of this electric field intensity. We can also calculate the dimensional formula. So this is the dimensional formula of this electric field intensity. We can use the calculate the dimensional formula using the dimensional formula of force here. We know the dimensional formula of force is nothing. It's m1 L1 T minus 2. This is the dimensional formula of force. And the charge Q naught. We know we can replace the charge Q by current multiplied with the time. And the dimensions of the current is ampere to the power 1. So we'll get m1 L1 T minus 2 here upon A1 T. So finally, we'll be getting the dimensional formula here as m1 L1 A minus 1 T minus 3. So this is the final dimensional formula of electric field intensity. Electric field intensity. The amount of electric field produced, the magnitude of the electric field produced, it depends on the charge. Greater the value of charge, greater will be the strength of the electric field produced. So electric field produced is directly proportional to the charge Q. So as we increase the presence of this charge Q, magnitude of this charge Q, electric field intensity is going to increase. It's going to increase. So more the charge present, more the magnitude of charge present in a space, the more will be the electric field intensity because of that charge. And more will be the force experienced by any test charge which is placed in the space of that charge plus Q. Now let's define what actually the test charge is. The test charge is nothing. Suppose that we have a charge plus Q here, and we are placing a charge plus Q naught here, which is a test charge. And this charge Q naught is a test charge. This charge Q naught is a test charge. And we want to find the electric field intensity at this point near this charge Q naught. Let me define this position vector by R vector, and it will be nothing R into R cap. Here R cap is the unit vector along this direction, right? So it will be the unit vector along this direction, vector R. We know now there are two charges present. The first charge is plus Q, and another charge is plus Q naught, which we call as test charge. But the question is that we have to find the electric field intensity because of this charge. We want to find the electric field intensity because of this charge Q. This charge plus Q is going to have some electric field intensity because of itself. But if we place a plus Q naught charge here, it will also produce some electric field at this point. It will also have its own electric field. It will also have its own space around it. So if the presence of this charge Q naught also produce some electric field intensity, then the net electric field intensity will be different than the electric field intensity of this plus Q charge. But actually we want to calculate the electric field intensity because of this charge. So what we do is that we define a test charge. The test charge, it's a very small charge, very small charge. It's a very small amount of charge which does not interfere with the electric field because of this charge plus Q. The electric field produced by this charge Q naught, it's so small, it's so small such that it does not interfere with the electric field of this plus Q charge. So we can say that the electric field intensity produced by this charge plus Q naught is negligible as compared to the electric field produced by this plus Q charge. So that when we calculate the electric field because of this plus Q charge, the net electric field will be given by the will be calculated because of the presence of this plus Q charge only, this one. So that's why we define the test charge. So it's not like test charge is some unit charge. It has got some important significance to define here. The significance is that it should be a very small amount of charge so that it does not interfere with the electric field of other charge which is placed near it. So that's the significance of test charge, that it does not produce a significant electric field. The electric field produced by this charge Q naught, which we call as test charge, it is very small and it does not interfere with the electric field produced by the charge plus Q. So that's what we understand by the test charge. So electric field, once again, we said that it's a function of a position vector. If electric field is a function of position vector, suppose we have plus Q charge and the field at this point is suppose E1, and at this point the field will be E2, and at this point in different direction the electric field will be different. So we said that it depends upon the position vector. So if we want to find the electric field at this point, suppose if we want to find the electric field at this point, that's the point Q, point P. So it will depend the position vector of this point P from this charge plus Q. And let me call this position vector as R1. And let me call this position vector at point Q as R2. So the electric field, suppose that here electric field at point Q is E2 and the electric field at point P is E1. So the position vector of both the points is different. R1 is different than R2. We say that R1 vector is not equal to R2 vector. So definitely E1 vector is not going to be equal to E2 vector. So we say that it's a function of a position vector. For different position vectors, the electric field intensity at different points will be different. So that's why we say it's a vector quantity whose direction is always in the direction of force experienced by a positive test charge. The direction of electric field intensity is always along the direction of force experienced by a test charge. It's always directed along the direction along which the force is experienced by the test charge. Suppose that this is the charge Q here plus Q, and this is the test charge placed here Q naught. If the force experienced by this plus charge Q naught is in this direction, this is the force experienced by this charge Q naught. So same will be the direction of this electric field intensity because of this charge plus Q. And this force will be nothing. It will be equal to electric field intensity charge multiplied by the electric field intensity at that point. So E vector is nothing. It's equal to F vector upon the charge Q naught. Upon the charge Q naught. Now let's try to understand how the electric field is produced by different charge. How the electric field is produced by the positive charge and how the electric field is produced by the negative charge, negative point charge. Suppose that we have a plus Q charge here. It's a point charge. The electric field produced by the point charge, it's a point charge. Plus Q, it's a point charge. It's a point charge. Electric field produced by the plus Q is always, electric field due to the positive charge is always originating from the positive charge and is always directed away from the charge. Electric field due to positive charge is always directed away from it. And if there is no charge present in the space of this plus q charge. In the space of this plus q charge. So we call this charge as isolated charge because there is no other charge present near this charge or around the space of this charge. Then the electric field produced by this plus q charge, these will be the straight lines going away from this plus q charge, and it will be radially outwards but spherically symmetrical. Spherically symmetrical. These electric field lines, because of this plus q charge, these electric field lines are going to be straight lines away from this plus q charge, radially outwards and spherically symmetrical. So they will be away from plus q, away from plus q, radially outwards, radially outwards and spherically symmetrical. And this is only possible if there is no any other charge present in the space of this charge plus q. That's the reason we call this charge as isolated charge. Isolated charge means this is the only charge present here. So it will be the electric field because of this plus q charge will be radially outwards and spherically symmetrical. Spherically symmetrical. What does it mean that spherically symmetrical? Let's try to understand. Let's suppose that this is the sphere here. This is the sphere here. And at the center of this sphere, I'm placing a charge q, and suppose the radius of this sphere is r. Then the field because of this charge q, electric field lines or the electric field because of this charge q, it will be radially outwards like this in all the directions, in all the possible directions. Spherically symmetrical, that's what do we mean by the spherically symmetrical? So this electric field will be distributed in 3D space, three-dimensional space. It's not a circle here, it's a sphere here. It's a sphere here. So that's what do we mean by the spherically symmetrical? It means that on the surface of this sphere, on the surface of this sphere, suppose this is the point P and this is the point Q, and I call this point as R. The magnitude of this electric field because of this plus Q charge will be same at every point on this sphere, that's P, Q, R and any other point. But the direction of electric field intensity will be different. We can see that this direction is different direction and this is different direction. They are directed along different direction at different points, but spherical, symmetrical, radially outwards. If this is the E1 vector here, if here the electric field intensity is E2 vector and here the electric field intensity is E3 vector at point R, then we can say that E1 vector is not equal to E2 vector, is not equal to E3 vector. But since this is isolated charge, isolated point charge, there's no any other charge present near the space of this plus q charge. And the field because of this charge is spherically symmetrical. So we can say that the magnitude of electric field, magnitude of this electric field intensity on the surface of this sphere is going to be equal. The magnitude of this electric field is going to be equal, is going to be same on the surface of this sphere. So that's what do we mean by, what do we understand here by spherically symmetrical. So the electric field because of plus q charge is away from the charge and is always radially outwards. These are the straight lines radially outwards, provided there is no charge present near the space of this plus q charge. Near the space of this plus q charge. Now let's try to understand what will be the how the electric field lines or the electric field will be because of the negative charge. Let's suppose that we have a minus q charge, that's a negative charge here. It's also isolated. Once again, isolated charge. Isolated charge means there is no charge near the space of this minus q charge. It's an isolated charge. There is no charge near the space of this charge. The electric field lines, because of the negative charge, it will be always towards the negative charge. It will be once again straight lines, but it will be directed towards the negative charge. In case of positive charge, the electric field was directed away from the positive charge. But in case of negative charge, the electric field is always directed towards the negative charge. So this is how the electric field lines will be because of this negative charge, directed towards this negative charge. These are the electric field lines because of this negative charge. Now the concentration of these electric field lines, electric field, depends upon the magnitude of this charge Q. So more the charge, more the magnitude of charge, more the magnitude of charge, greater is the intensity of electric field. तो जितना ज्यादा चार्ज की वैल्यू होगी उतना ज्यादा इलेक्ट्रिक फील्ड की इंटेंसिटी ज्यादा होगी. ग्रेटर इज द इलेक्ट्रिक फील्ड इंटेंसिटी. More the charge, value of the charge, more is the electric field intensity. So this is how the electric field lines will be because of this charge minus q. Once again, it will be spherically radially inwards. It will be radially inwards for an isolated charge. Radially inwards, not outwards. Radially inwards. Radially inwards, spherically symmetrical. So it will be spherically symmetric. So suppose that we have a sphere here and we are placing a charge q here. We have a sphere here and we are placing a charge q here. Charge minus q. The electric field because of this charge will be directed like this. So this is the direction of this electric field. It will be always directed along the negative charge, not away from the negative charge. It will be always towards the negative charge. Towards the negative charge. So that's how we draw the electric field because of the presence of positive charge, but isolated. There's no other charge. Will be later on discussing the other situations as well when we have multiple charges present. We don't have the isolated charge. There are other charges also present. Then how do we plot? How do we draw the electric field lines? That will be discussed later on when we study about the electric field lines and their properties. So till now, we got to know how the electric field lines, how the electric field varies for a plus q charge, isolated plus q charge, and the isolated minus q charge or the isolated negative charge. So for positive charge, the electric field lines are radially outwards and spherically symmetrical, and for negative charge, they are radially inwards. And one more important point is that force on a point charge is in the point positive charge. If we have a positive charge in some electric field, in some external electric field, then the force on positive charge is always along the direction of the electric field. Force on positive charge is always along the direction of electric field, but the force on negative charge is opposite to the direction of electric field. It's opposite to the direction of electric field. It means that Suppose this is the plus q, and this is the q naught here, that's plus q naught. And suppose that this is the electric field because of this charge q, then the force because of this charge, because of this electric field, because of the presence of this plus q charge, is going to be q naught times E, and it will be along the direction of the force. Along the force will be along the direction of electric field. But in case of negative charge, if we place a minus q naught here, and this is the direction of electric field because of this charge plus q, then the force experienced by this minus q naught, it will be in the opposite direction. So this will be the direction of force experienced by the negative charge. So for positive charge, the direction of force is along the direction of electric field. But for negative charge, the direction of force is opposite to the direction of electric field. So let's try to solve some of the questions related to electric field. Suppose a charge of 10 microcoulomb and minus 10 microcoulomb is placed in uniform electric field, 5 into 10 to the power 6 Newton per coulomb, directed along the positive x-axis. There is a uniform electric field. Uniform, by uniform electric field means that electric field is constant, it's not varying, it's constant electric field. Let's suppose that this is the electric field here. It's the representation of the uniform electric field, and the magnitude of this uniform electric field is given as 5 into 10 to the power 6 Newton per coulomb, and it is directed along the positive x-axis. And there are two charges placed in this electric field. Let me write those charges. Q1, that's 10 microcoulomb, and there is another charge which is a negative charge, that's equal to minus 10 microcoulomb. One is a positive charge, another is a negative charge. So there will be a force on this positive charge. We know that for positive charge, the direction of the force is along the direction of electric field. So this will be the direction of force. And for the negative charge, the force acting on it is opposite to the direction of electric field. Let me call this F2, this is F1. And we know that F1 vector is nothing, is the charge multiplied with the electric field. And the charge here is, for the positive charge, it's 10 into 10 to the power minus 6. And the electric field is given as 5 into 10 to the power 6. So it will be 5 into 10, that will be 50 Newton. But it is directed along the positive x-axis. So we can write it 50 Newton, that's but I cap. 50 I cap. So this will be the force vector that will be acting on this charge Q1. And similarly for this negative charge F2, the force will be, it will be minus 10 into 10 to the power minus 6 multiplied with the electric field, that's 5 into 10 to the power 6. So it will be once again minus 50 Newton, but it will be directed along minus I cap. It will be directed along the negative x-axis. So this is how we calculate the force because of the presence of external electric field. So this is the equation. If there is external electric field present in some field, in some space, then the force acting on the charge Q is given by the electric field multiplied by the charge Q. The direction of the electric field will give the direction of force. We have another question. Calculate the electric field intensity, which would be just sufficient to balance the weight of a particle of charge minus 10 microcoulomb and mass is equal to 10 grams. So we have a particle here. Suppose the mass of this particle is equal to 10 grams. So 10 grams is the mass of this particle. And there will be weight in the downward direction on this particle, that is equal to mg. M is 10 grams, so we can write it 10 into 10 to the power minus 3 kgs. And the value of g is given as 10. So it will be 10 to the power minus 1 Newton. It will be in the downward direction. And there should be an electric field. electric field should be in the opposite direction to balance it. If the electric field is in the opposite direction, and it must be in the opposite direction so as to balance this force due to gravity, because of this because of this electrostatic force which is present here because of the presence of external electric field, and we have to find the value of E, for which this particle of mass m will remain stationary here, or it will balance the weight of this particle. So if E is the electric field, then force on this, if the charge of this particle is the charge is given as minus 10 coulomb. The charge is given as minus 10 microcoulomb. If the charge is minus 10 coulomb, if the charge is minus 10 coulomb or the charge is negative here, so force should be in the opposite direction. The force acting on this particle of mass m should be in this direction. So this should be the force because of the electrostatic field. This should be the direction of force. But the charge on this particle is negative. But the charge is negative. That's minus 10 microcoulomb. So if we apply a field in this direction, if the field is applied in this direction, then only the force will be in the opposite direction and it will balance the weight mg. So field should be in this direction. Then only it is possible it will balance the weight of this particle, because the electric charge of this particle is negative and the electric force is always opposite to the direction of electric field in case of negative charge. So this F is nothing, it's equal to QE, and it should balance mg. So E will be nothing, it should be mg upon q. So mg we are calculated as 10 to the power minus 1, and q is nothing, it is given as 10 microcoulomb, that's 10 into 10 to the power minus 6. So it will be 10 to the power minus 5. So it will be 10 to the power 4 Newton per coulomb. So this is the amount of the electric field that should be applied in the vertically downward direction so that the net force on this mass m is balanced by the weight mg, or the net force on this mass m is 0. Net force on this mass m is 0. Let's try to solve this last question, and then in the next class we'll be discussing about the electric field due to a point charge. How do we calculate the electric field intensity due to a point charge? So the question is, a positively charged oil drop is in equilibrium in a uniform electric field. We have an oil drop here. This is the oil drop. This is the oil drop. A positively charged oil drop is in equilibrium. Suppose that the mass of this oil drop is m. Mass of this oil drop is m. And the charge of this oil drop is q. Charge of this oil drop is q. And there will be a force because of the weight of this oil drop, that will be mg. It will be always vertically downwards towards this ground, towards the surface of this ground. A positively charged oil drop is in equilibrium in a uniform electric field. By equilibrium, we mean that the net force on this oil drop is equal to 0. And if the charge of this oil drop is given to be positive, then it will be only in equilibrium if the force acting on this positive charge is in this direction or the electric field is in this direction. So this should be the electric field direction. The direction of this electric field should be in the vertically upward direction. And the force acting, electrostatic force, will be nothing. It will be QE. And this QE will be balanced by this mg. QE will be balanced by this mg. Now the question is that if suddenly direction of electric field is reversed, direction of this electric field is reversed. Now if we reverse the direction of this electric field, on reversing the direction of electric field, on reversing the direction of electric field, if we reverse the direction of electric field, It means that this is the charge q and mass m, weight is still downwards, that's mg. Now what we are doing is that we are just reversing the direction of the electric field. Now electric field is in the downward direction. Electric field is in the downward direction. If the electric field is in the downward direction, so the total force will be in the downward direction. There will be no force acting on this oil drop in the vertically upward direction. So all the forces will be in the vertically downward direction. So the total force acting on this will be nothing. It will be QE plus mg. QE plus mg. And we have to find the acceleration of this uh, oil drop. So the acceleration will be nothing. We know acceleration is nothing. It's F net, that net external force upon the net mass. The net external force acting on this charge Q is QE plus mg when we reverse the direction of this electric field upon the net mass m. So the acceleration will be nothing, QE upon m plus g. So the acceleration of this oil drop will be greater than the acceleration of due to gravity. So we can clearly see that it's g plus QE plus m. So acceleration here is greater than g. So it's clear that acceleration of this oil drop is greater than g. So it will be accelerating more when we reverse the direction of electric field in this case. So we'll stop here and we'll be discussing electric field due to a point charge, and all this discussion will be for the next class. And we'll be discussing it in detail, and we'll be also discussing the electric field lines and the properties of electric field lines in the next class. And not only that, we'll be discussing how to plot, how to draw the electric field lines to the presence of many other charges, due to the presence of many other charges. Till now, we discussed about the electric field directions of positive charge and negative charge, but both the charges were isolated. There was no presence of any other external charge. So that's it for today. We'll be discussing all these things in the next class. Till then, take care and goodbye.